Thank you for coming. Happy Thursday. So our plan for today, we're gonna look at Fleury's algorithm, and then we'll talk about Dijkstra's algorithm. I've got a video for us to watch for Dijkstra, and that I found that is good. If you are in 374, it's a different video. Um, so yeah, I like it. And so we'll do that. We'll have some practice problems. Then we'll talk about the Chinese postman problem, which is also related to both of these. Okay, that's enough for you. That's for you. Okay, so last time we looked at minimum spanning tree algorithms. So how, given a graph, how can we find, given a weighted graph, how can we find a spanning tree with minimum cost? So we looked at several algorithms to do that. Now we're going to approach a slightly different problem. So the problem is paths. So how do we find a path from one place to another place in the graph? Preferably, since we're working with weighted graphs, with some minimum cost. So we're going to first look at how do we find an Eulerian trail, then how do we find the shortest path from A to B, or A to everything, depending on how we frame the problem. And then we'll look at the case study. So you'll recall that an Eulerian trail, remember when we talked about Eulerian and Hamiltonian graphs? Hamiltonian is the one with the cycle that touches all the points. And then the Eulerian trail is a trail that goes through every edge of the graph. So we traverse every edge. And so maybe that means we visit vertices multiple times. That's okay. What matters is that we get every edge. And so we've got a definition for that. So for a graph to be Eulerian, for that trail to exist, we need a graph where every vertex has even degree. So those are two definitions that we need to remember for today. So there's an algorithm to find an Eulerian path. So before we kind of maybe we're just going by vibes to try and find this path, but there's an algorithm to get there. And so we start with this Eulerian graph and we choose a vertex to start with. This can be arbitrary. And we're going to start from the current vertex and traverse any available edge and record that. When we choose any available edge, we're going to choose one if the edge available is a bridge and there's no other options, then we take the bridge. So remember, a bridge is, so if this is our graph, a bridge is an edge who, if we remove it, the graph gets disconnected. So this is a bridge, that edge. If we remove it, then it's disconnected. But for example, an edge like this one, if we remove it, it's not disconnected. So it's not a bridge. So when we're choosing an edge, we only choose a bridge if there's no other option. And then we erase it and any isolated vertex that comes along with it and continue. So starting from wherever we are, we choose an edge and traverse it, go to the other vertex, delete that edge. So we go through the graph this way until there's no more graph, and then we've got our trail. Okay. So let's do an example. So in this example, we start with U. Let me see. Okay. So we're going to start with U. And we can, so there's many options that we can take. The one that the book takes in the example is the edge with A. So since none of these options are bridges at the moment, we can just choose one and go along with it. So let's say we choose A. And so then we write U and A. And so now this edge is deleted. And our graph looks like this. So then now we're at A, and we can repeat this second step. So starting from the current vertex, traverse any available edge. If we're right here, there's only one available edge. So we take that. So we write down, now we've taken the edge from A to B. And now AB is deleted. Now we could go back. So now we're at that point. From here, if we wanted to go back to U, we technically could, but that's a bridge now. And so we can't take that because we've got other options. So we could go to D or up to C. I'll go up to C. And so this continues. So we go down to U to D. And so now our graph looks like this, and we're right here. And so now we do have to take the bridges because there's no other option. So we go across to B, write that down. We go across to U where we started, write that down. And so now we're back at U. And so now we can go around the triangle any way we want. So I'll choose counterclockwise. So F, E, and then back to U. And then once we do that, we're done because we've gone through the whole graph. We've erased all those edges and we've found this Eulerian trail, which is UAB, CDB, UFEU. That's our trail. So that's our algorithm to go through the graph. Okay, so now you pull out paper and pencil. It's your turn. So the only requirements is that you start with the edge UV and then VZ, just to kind of narrow it down a bit. Well, you get all that set up. I'll do attendance. All right. Tell me what trails you found. So if we start with U, V, and Z, what comes next? XWT. Cool. Others? There's multiple options here, right? Or did we all get the same version?
From the UBZ to T, W, V, E, Y, W, X, Y, U.
Wait, Y, Z? Okay, wait, so UVZ. I think UVZY.
UBZ, T.
Yeah. Yeah, no, I think this one is missing some. Yeah. No, that's okay. Okay, so you go UVZ and then TW, V, back down to T, down to Y, and then get rid of X. Wait, no, Y, X. I don't see how that's possible.
YW.
Y. Okay, so V T Y W X. Wait, hold on. U V V T W V T Y up to W down to X. Oh, okay, yeah. Yes. Okay, I'm sold. Other paths that you found? Yeah.
So the UVC and then TVW, TYW, XYZ.
Yeah, okay, so I think the only difference here is you went one of you went this way around and the other you went that way around. So, cool. Yeah, so there's multiple options. All right, so that's Fleury's algorithm, which gives us this path. There's another path algorithm. The book never says that it's Dijkstra's algorithm, but it is. So I'm not sure why they don't name that. There's a lot of pseudocode for this one. So we're gonna try and read through it, and then we'll watch a video that explains it much better than all of this. So to start with, we're gonna assign, so we've got some sort of network here, and we're gonna assign the potential, saying this is the distance or whatever the weight is to get to this vertex from the start vertex. So typically we'll denote one vertex as the start, and we're trying to find what's either the shortest path to an ending vertex like T, or what's the shortest path to every other vertex in the graph. So that's the goal. We want to find its the shortest path algorithm. And so to start with, we say, okay, the vertex that we're starting with has potential 0 because if we start here, then it takes no effort to get here. So that's our kind of trivial starting step. So each vertex is going to have some potential to say, here's how much effort or time it or distance it will take to get from here to some other vertex. And this pseudocode calls that the potential. So just that shortest amount. And so the general step is we consider all the vertices that we have assigned a potential. And so initially we say that you'll see some other algorithms where every other vertex is like infinity distance away to start with. Say they're very far away. We don't know how to get there. We hope that we'll figure it out as we go. So to start with, let me move this down here. So to start with, we say, okay, wherever we start, it potential 0. So among the vertices just assigned a potential, which initially is just S, we consider every vertex that we can get to from S. So where can we go from here and we find the edge weight plus whatever our potential is. So for the vertex that we're looking at, we find, okay, what's the potential of V? So what's the distance to get here? And then add the distance of the edge. So over here, if S potential is 0, then we look at all the things we can reach from S, which include A, B, C, and D. And For A, there's an edge of weight 7. So now it takes 7 to get to A. For B, it takes 4. For C, it takes 9. For D, it takes 7. And so these are all secretly 7 plus the potential of S, which is 0. So that's the general step. When we label all those possible vertices, then we have to choose a vertex to look at next. And so we'll look at the all the options and we'll pick the smallest. And then, so the smallest vertex labeled that is not already a potential, and make it a potential at each vertex where it occurs. That's wordy. We'll look at the example. And so we repeat that, and then we stop when we get to T. We'll stop when we say this is the shortest path to get here. Yeah. Okay, let's watch the video. Okay, I'll pause recording, but I'll put the link in here next to the video link, just because it's not my video. Okay, so let's try this out. I think, let's see, I want to keep the annotations, but I want to do it in here because then I have easy access to an eraser. So yeah, and so this is the algorithm that I recommend. You use a pencil. I typically like to do pen, but yeah, since there's a lot of updating things, yeah. Okay, so I'm also gonna have some sort of table over here. So I'm gonna have, so if we have vertex and the distance and the, let's call it previous. And so I'm gonna say S is in my table, so is A, B, C, and D. Could also have created an actual table in the spreadsheet, but that's fine. Okay, so we've got this, and so we're starting at S. So the distance to S is 0, and it's no previous because that's where we're starting. And so we look at the things we can reach from S, which are A, B, C, and D. And so we go through and update those values. So to get to A, it's a weight of 7. To get to B, it's a weight of 4. To get to C, it's a weight of 9. And D is, again, a weight of 7. And so all of these, we come from S. So we just write that down. In the video, they like marked it on the graph, but we can also keep track of it in a table. All right, so once we've done all of that, S is done. And so now we look at the options. So among all of these numbers, which one's the smallest? And that would be B with 4. So now we look at B. And we ask, what are the places we can get to from B? That includes A and C. So to get to A, it would be 4 plus 1, which is 5. 5 is better than 7. So now we erase what we had for A. And so 4 plus 1 is 5. And we got there through B. So that's where we get that number. So either we could, since we get to B through S, we can leave that, or if we just want to say this is its direct source, we could just have that too. Okay, so we've updated A. Let's update C. So 4 plus 3 is 7. 7's better than 9. So we do the same thing. So that's 7, and our source is B as well. We can't get to D from B, so we're done with B. Okay, so now we look at our unexplored values, 5, 7, and 7. We choose the least, which is 5. So now we look at A. So, oh wait, I forgot T in here. T is initially infinity, and we can't get there yet. But now once we're at A, we can get there. So the weight of A, 5 plus 6 is 11. We can get to T with weight 11 coming from A. And that's the only thing that A points to, so we're done with that. All right, so then out of 7, 7, or 11, we choose one of the 7s. Let's choose C, just so we can go in alphabetical order. And so from C, the only place it goes to is T. And so let's see if we can beat 7 plus 3, which is also 11. So,
I think that's
wait. You're right. I can't do math. Yeah, it is 10. You're right. Thank you. So now we come from C instead. Okay. And that's the only way that we can go from C. So we're done with C. And then we look 7 or 10. We choose 7. And so from D, we can go to C or T. To go to C, it would be 7 plus 1 is 8, which is not better than 7. So we leave it. And from D to T, it would be 7 plus 4. That is 11, which is not better than 10. So we leave it. So we're done with D. And then we get to T, and there's nowhere we can go, so we're done. And we have our final score of 10. And so now we can say, starting at T, we can go back to C, and then from C, we came from B, and from B, we came from S. And that's our shortest path. Questions on that? Cool. All right, so now I've got one for you to try. So assuming that we go in general, I think I tried to do some research on why the shortest path goes from S to T, like why we have those letters. I haven't found anything yet. If you find it, let me know, because I'm curious. But typically in graph problems, if we're going from somewhere to something, we call the source S and the destination T. Source and target. And yeah, that makes sense. Just my brain didn't give me those words. I see. Some people still looking up and down. Who's done? Okay. Maybe 30 more seconds. Okay. Someone want to give me the shortest path? Yeah.
I got SBFT.
B to F and then up to T. Did we all get that? Cool. All right. I found this GIF or possibly GIF when I was on the Wikipedia page of this is how like a robot is trying to figure out what's the shortest path to get there by exploring all these possible options. So it's kind of like a wave as it goes, and it figures out, oh, this is not possible. I can't go any further. And so it kind of goes around that. And it keeps going, keeps creeping until we reach a point where this is the shortest or the smallest option to go forward. And so then we realize, oh, we're done. We found the shortest path. So I think that's cool. One of the other things that is interesting, if you take a communication networks class, which is basically how does the internet work, one of the things they'll talk about at some point is like, what's the shortest distance to route the packets from this place to the other place? And it'll do Dijkstra's algorithm. And so it goes over this again in that class as well. Okay, so there's a problem that the solution to which kind of combines these two algorithms, which we talked about today, which is the Chinese postman problem. And the problem is a postman wishes to deliver mail along all streets in his area and then return to the depot. How can he plan his route so as to cover the smallest total distance, right? So still minimizing. It's called the Chinese postman problem because it was developed by this guy. He did it when he was 26 years old in 1960, and it's called the Chinese problem because the um, people in other parts of the world saw he like published it in Chinese in this like local journal, and so they saw that, and it was an interesting problem. And since it was in Chinese, they labeled it the Chinese postman problem. I found an interview that they did in 2017 with him, and I thought it was pretty cool because he talked about how like he proposed this problem at age 26, and he's done all these other things since then. He's like president of a university and all these things. But the thing he's still most known for is what he did when he was 26, which is propose this problem. Okay, so our rephrasing of this is we want to find a closed walk. So going along the graph, maybe not finding every edge, but going around the graph of minimum total weight, or that actually it does include every edge at least once. So, oops. So the solution here is it's a mix of both shortest path and Eulerian trail. So if the graph is Eulerian, then we've got no problem where we can take all the edges, come back to our starting point. That's no problem. But if it's not Eulerian, that means that there's some vertices with odd degree, and so we need to figure out how to handle those as well. And this is where the at least once thing comes in. If we can get it down to once, then that's great. But if we have to take it multiple times, then we can do that too. So the way we solve this is that by the handshaking lemma, the number of odd degrees has to be even. So the number of vertices that have odd degree, that number should be even. And so since that number is 2 multiplied by something, then we want to double the edge along these. So we'll take the pairs of odd vertices and we'll double the edges along the paths between those pairs. So that's where Dijkstra comes in, where we want to find the shortest path between these two pairs and then just double the edges along that path. Once we do that, we use Fleury's algorithm to find that trail. So the way that doubling looks is if this is our graph, we've got V and W. Those are our vertices with odd degree. So 1, 2, 3, 1, 2, 3. Everything else is even. And so we find the shortest path between V and W. That's Dijkstra's. And then we just double those edges. So instead of just one edge of weight 3, we make 2. And just assign it the same weight. Okay, so let's try this one. So if we've got our corrected graph, then this is the other thing. The book doesn't like go into detail that much about this problem. And then okay, so we find the shortest path, and then I think the goal, which they didn't state very clearly, but the goal is to go from A all the way around back to A. And so this is where Fleury's comes in. And so from here we can maybe choose between 2 or 5. We take 2. And then 6, 2, or 1. We'll take 1. And then maybe 1, 2, or 4, maybe back along 1. And then 6 or 2, we take 2. 3, 4, maybe take 3, and then now we go back to 2 and down 4. So just doing Fleury's algorithm to find that trail. And then from here, we could either go to W and back or go back to B. We've got options. So let's go back to B, go down here, take the 3 there, take the 3 back, and then back to A. So here's the issue where the book's not specific on what it means for like minimum cost, where I think maybe the minimum cost occurs in the Dijkstra's finding the shortest path between those 2 odd vertices. Because other than that, the problem is to include every edge at least once. And so how minimum total weight factors into that, I don't know. I think that's a shortcoming of this one. But yeah, so that's the Postman problem. Any thoughts on that? Yeah. So I think it depends on how we phrase it. So the book says find a closed walk of minimum total weight that includes every edge at least once. And so I guess like if we interpret these as streets, then we need to like visit every house on the street and not just visit every intersection. But there may be multiple framings of it. So like one of the variations is like if we're snow plowing, then we need to, if we need to cover both sides of every street, then we need to double the edges. So that we like, you don't just go one way on the street, you also need to go the other way. But yeah. Other thoughts? Okay, so I'll have you try. So this is a graph that has some vertices with odd degree, so B and C. So we want to find, first of all, which edges should be double, and then run Fleury's algorithm. Let's see. Solution in the book for this problem is also wrong. The book says there are two vertices of odd degree, C and F. I'm like, there's no F. So, oh well. Okay, so what's the shortest path between B and C? Literally any of them, I think, because we could go just 7 or 3 and 4, that's 7. Or around A, E, D to C, that's also 7. Is there a faster one? Yeah, something B, E, D, C, 3, 5. Oh, wait, yeah, you're right. 6. That is 6. Anyone find a faster one? Is that it? Cool. Cool. Does anybody have the trail or the walk? I guess it also depends. It's also not clear where we start with this. Maybe we start at A. Or if you started at a different spot, then I think that's also okay. So let me know their trail when you get it. Sure.
E, E, D, E, C, E,
Wait, DEC.
A, E, E, C.
Yeah, cool. Okay, so the thing about this problem is that once we have the Eulerian graph, once we've got this closed trail, that's the optimal tour. Um, a variation on this, which I think is interesting, is if the graph is directed, then we can have this idea of the windy postman problem, where maybe you don't want to walk directly into the wind. You want to walk with like the wind at your back. Yeah. And so that's a variation on that. Okay. Another variation is the snowplow, where we need to cover both sides. And so for once we have this Eulerian graph, we just double the edges and then we're good to go. Okay, so we've got 9 minutes or so. So I've got extra practice. We have options. So we could do Dijkstra's or the Postman problem again. Who votes for Dijkstra's? Or who votes for Postman? We're gonna do one of them. Okay. Votes for Dijkstra's. One vote. Who votes for Postman? More votes. Okay. So let's do this one. There is some Dijkstra's in Postman though, so. So I think this one is nice because they're all even. Do we have a solution for this one? Any ideas? You gave me the answer before. Somebody else have an answer. Go for it.
So I tried S B A D C D to C D N S.
S B A D C T D A S. But I think we're missing, so I think that's, so we're missing like this street and this street. Do we have another solution that hits all of them? Give me yours if you've got it.
S A B C A D C T D E S.
So S A B C A D and no C T D B back to S. Cool. All right, 3 minutes. Let's do one. So now do Dijkstra's, or give me the shortest path from S to T. 9 + 2 is 11. 9 + 2 is 11. Okay. I'm almost there. So I'm guessing this is gonna give us the answer. So. Oh, wait, yeah. Okay. Does someone get it? I didn't quite get there. Sure. SAEFT. Yeah, so yeah, I was getting there. Cool. All right, thank you. So there's no homework for this, but there is still the homework from the stuff on Tuesday. So make sure you're working on that and work on your project because I'm expecting a paragraph or so progress report by tomorrow night. Let me know if you've got questions. Otherwise, thank you for coming. See you next week.